Yeah, thanks for the introduction. I'm, as you said, one of the drivers behind Traffic Server in the Apache community. I was actually sort of in charge of this at Yahoo 2-3 years ago when we first did this. So I've actually done a fair amount of work in the open source community to get this open source, and I'm going to talk a little bit about that too. I'm currently working at GoDaddy as the principal architect for all the web hosting services for GoDaddy, which is quite a challenge, of course, because dealing with millions of users and people doing crazy stuff is quite a challenge. So let's talk about the software first, where it came from. So Traffic Server has actually been around for quite a while. It came to be in existence around 1998 or 1999, something around there. And it was a commercial piece of software from a company called Inktomi, which is since then defunct. But Yahoo ended up acquiring Inktomi in 2003, I believe it was. And as part of that acquisition, Yahoo also acquired all the software that came with the company. And Traffic Server was one of those pieces. Unfortunately, what happened was Yahoo didn't really care about the software at all. They cared about the search engine stuff. So we shelved the software for about 2 or 3 years. And in 2005, I was chartered to basically build a CDN for Yahoo. And I've used many proxy servers in the past, like Squid and whatnot, and have sort of a little bit of a love-hate relationship between me and Squid. So someone pointed to me to the Traffic Server software, and I started looking at it, and I sort of compiled it and tested it and got it running on Linux. And it blew Squid out of the water right out of the box, which was pretty neat. So we did that. We built the CDN. It took us about 3 months to get into production and 6 months to be pretty much all migrated over to our own CDN from the commercial CDN vendors. And a part of that, we actually ended up thinking, hey, this would be a really cool solution to open source. And Yahoo back then was, when they still are, was really huge on open source. And we spent about 2 years trying to open source this sucker. It turned out to be a lot of work. It's amazing how many legal obstacles and lawyers and patent bureaucratic stuff you have to deal with, right? So you would think it would be easy to do this, but if any of you guys are looking at doing open sourcing stuff, I would highly recommend that you start off open sourcing from the beginning, because trying to take an existing piece of software like this and make it open source, it's a huge amount of work. However, we succeeded, and in 2009, we open sourced this with Apache Software Foundation. In 2010, we became what's called a top-level project. That means that we sort of a self-sustained, self-managing community within the Apache Foundation. And obviously, since then, we've been doing a number of releases. So there's always a whole lot of proxy servers out there. There used to be only one. There used to be Squid, right? And that's the only choice you pretty much had. Since then, there's obviously Apache Traffic Server, but there's also Nginx is a great proxy server. HA Proxy is fantastic. I think it's an awesome proxy server. Varnish is pretty good. If you use Apache HTTPD, you might be looking at Mod Proxy. There's also some things in Perlbal, and there's some stuff for Node.js to do proxy. So there's a lot of sort of options out there to do proxy servers. And when I personally look at this, obviously I pick Traffic Server by default, but if I were you, when you look at this, you need to sort of, heck, what am I looking for here? Why am I doing this, right? So you would do something like this slide here. And this is a slide that always causes problems, because I put it up here, and someone out there is wildly familiar with Nginx and say, hey, he's wrong on these 3 items or whatever, right? So take this for what it is. This was sort of an attempt to me to show you how I would look at my problem and say, what do I need out of this? Do I need reverse proxy? Do I need transparent proxy? Do I need all these things? Like, do I need ESI? And then make this matrix and figure out which of the proxy solutions is going to be the best for your particular problems. And this is important, right? If you don't know what you're trying to solve or what needs you have, you're going to pick the wrong proxy server most likely. So performance is obviously one of the sort of key criteria people look at. But the thing is today, most of these proxy servers are already sort of outrageously fast. You look at these numbers, right? We're talking about 100,000 requests per second or more. And who's going to run 100,000 requests per second on a single box? There will be Yahoo and Google and Facebook and a few other players, right? Most of you guys, that's sort of irrelevant. Now, you probably want to deal with it and make sure that you can handle traffic spikes and that sort of. But to me, it's much more interesting to look at things such as, latency, right? So when you compare latency, that's where the big winners are today. If you're looking at, say, in this test, I saw a difference of about, 2 milliseconds latency per request. Doesn't sound like a whole lot, right? But if you add this, let's say you're doing 50 objects on a typical page, well, now you're looking at 100 millisecond difference in latency on the page load time by the choice of proxy server. So those are the sort of things you would also need to take into consideration when you're picking your proxy server here. I also sort of jumped the gun here a little bit talking about proxy, which type of proxies there are. So let's go back a little bit and talk about the different types of proxies that you typically would use. And when people talk about proxy servers as intermediaries, there's typically only three types of proxy servers you would consider. The first one would be what's called a forward proxy. And a forward proxy would be a user tells his browser to use the proxy server to send all the HTTP requests through this proxy server. The proxy server is then allowed to do different sort of content manipulation if he wants to, or rewrite URLs, or just send it up to the website as it is. It can also cache the content, right, which is important. Typically, if you're doing this, you're doing it to save network bandwidth. But you might also do it to, say, control which websites your users can go to. The second type of proxy, the one that I'm personally most interested in, this is what you would do if you're doing, say, a CDN or accelerating your website, and that's what's called a reverse proxy. In a reverse proxy, the browser is agnostic. It doesn't know that it's talking to a proxy. To a proxy. The browser thinks that it's talking to any other regular web server, an HTTP server. The reverse proxy here is sort of a magical little device which goes in and looks at the request and makes a decision. This particular request for this particular resource should go to server A or B or C, right? And these decisions can be made on the URL, it can be made on cookies, it can be made on anything that you sort of configure the reverse proxy to do. As a good example would be here to say, let's say you want to do an A/B testing setup here on your website. You're doing a new version of your website, and you want to send some number of your users to this new website, but not all of them, right? You don't want to take out the whole site. So what you could do then is say, for all cookies that matches this particular regular expression or hashes to a particular value, send those users to a machine B, which is the sort of new version of the website. And this way you make sure that the same users go to the same machine or the new site all the time, and it's a much better user experience. You can do other things like, say, URL hashing, where you want to make sure that all URLs matching a particular pattern goes to a certain machine. That could be better for things like cache locality. Maybe you have a memcached local on the box or a MySQL local on the box that has the data in memory. It would be beneficial that all requests for a particular URL ends up on that particular machine. This is a very powerful tool, right? You have a lot of options you can do here. But even in the simplest form, just putting a reverse proxy in front of your website can do things like caching content and do keep alive over long periods of times and that sort of stuff. And the last type of proxy that people sometimes use is called an intercepting proxy or transparent proxy. And this is sort of a mixed bag of pros and cons. Basically what happens here is that the proxy sits between the user and the websites, and the user has no choice here by going through the proxy. It's done by the routing magic or by the firewall or whatever you might be using, right? And you're sort of forcing your users to go through the proxy. And this is maybe considered evil sometimes because maybe you don't want to go through a proxy, maybe you have privacy concerns, or maybe some proxies don't work with certain sites and so on and so forth. Typically you will see this sort of setup done for ISPs who want to force all the users to go through a proxy, and they do this to save bandwidth, right? They want to make sure that all the users go through their proxy, caching proxy, to fetch the YouTube content, and then they can do some interesting things with caching that content, and they save a lot of bandwidth, right? So a lot of money to save here in their space. But when we talk about proxies, typically what people think about is caching, or, well, not that sort of cache, content cache, right? You want to cache the content that's possible to be cached on the edge. And the idea here is that you want to make sure that your content gets out to these proxy machines, to the edge nodes, as close to the users as you possibly can. And this makes things much easier to manage. Your server is a whole lot easier to manage now, right? Setting up a cache is fairly straightforward. If you lose a cache, if the disk crashes or whatever, you haven't lost anything because it's just a cache. So you can rebuild it, put in a new one in there, and it's still the content just sort of automatically appears on these cache nodes. And you get better performance, a lot easier to scale, a lot of big wins here to cache the content, right? Now the key here is, of course, the content has to be cacheable, so that's a bit of a problem in its own. But as long as you can cache some of the data, it's going to be a win. And so why is that a win then, right? Why is it so important to cache the data? Why is it so important to cache this out on the edge nodes? Everyone talks about edge. Everyone knows what the edge is, right? The edge is basically, if you're seeing this big cloud, that you have machines that are close to the edge, means that they're close to the users. And what that means is that they have a short round trip time from the users down to the servers. And this is important for many reasons. The first one is three-way handshake, right? If you know TCP does always a three-way handshake on every connection. What that means is there's always at least one round trip of time of latency before you can start doing anything on that connection. And you can imagine if your round trip time now is from the user to the mob, to the machine itself, to the proxy or to the server, is say 100 milliseconds, that's an instant 100 milliseconds latency on that request before you can get anything. And think further away. Let's say you're in India, and you have users in India hitting your data centers in the East Coast. You might be looking at 200 milliseconds or 300 milliseconds. Significant amount of time just to set up this TCP three-way handshake. And I'm not going to go into details why that is, but it's just the way TCP works. It has to basically negotiate the setup of the connection. The second thing that people might not be too familiar with, everyone knows about three-way handshake. It's sort of the obvious one. It's really easy to see and detect. But the other one is congestion control. TCP enforces congestion control on you. And the reason for that is to avoid flooding networks or poorly behaved networks or networks with a huge amount of packet losses, to sort of take those down by sending too much data on them. So it's sort of a self-regulating way of negotiating how much data you can send out on the wire. And the typical today is that you start off with what's called an initial congestion window of 3 packets. And what that means is the server can send no more than 3 packets on the wire before he has to wait for an ACK back from the client saying, hey, I received these 3 packets. Well, here's the problem, right? The same problem as with the three-way handshake. If your latency is 100 milliseconds, you're going to see for every round trip here, there's an extra 100 milliseconds. So if it takes 3 round trips to get your data to the client, you're looking at 300 milliseconds just to do that. Huge amount of time, right? Now, the window will grow exponentially by the way typical protocols are implemented, but they always start off fairly small. So here's a key thing. So you want to solve this. You want to make sure that you avoid this. And the 2 things you can do, and both things the proxy can do for you. One is to put the proxy servers close on the edge, where the round trip time from the user to the proxy is short, maybe in the order of 20 milliseconds or instead of 200 milliseconds, right? And the second thing is proxies can more easily do what's called HTTP keep alive, persistent connections from the client to the server. And as long as you keep pumping data on this keep alive connection, the congestion window, which is grown up in the first sort of 2-3 round trips, stays that big, right? So continuous request on that pipe will continue using this large congestion window size. And this is huge, right? Now you can start sending maybe entire HTML pages in one blast without waiting for an ACK. Or if you have JavaScript and images and whatnot, they can do the same benefits. So congestion control is a huge enemy, a big problem. And that's the one you're going to see the most benefit from, honestly. We did benchmarks for this when I was back at Yahoo, and simply putting a proxy in India in front of basically Yahoo's website, the search page, they would see page load times drop from in the order of 2 to 3 seconds to less than 1 second. Just by doing keep alive persistent connections over the long haul between India and the US, and then have clients doing connections to the proxy in India, local in India, which is a short round trip time, right? Huge amount of improvements for very little effort. I mean, setting up a proxy server, anyone can do that. It's really easy. The last thing that's going to be a problem is DNS lookups. And this is sort of a hot potato where some people say that you should put lots of domains on a site to get more sort of parallelism. The downside to that is that you're going to see, in this case, let's say you're making a website, right, where you mesh content from news and finance and groups in this particular example.com site, well, you're going to have to do 3 DNS lookups. Each one might take, say, 50 milliseconds or 80 milliseconds, so some significant amount of milliseconds to do a DNS lookup, right? And those are latencies that you can't really do anything about. So that's where you see people doing things like this. And you probably recognize this from, if you go to Google, for example, right? You go to calendar.google.com, well, it rewrites that and you end up at google.com/calendar. Well, a proxy can do that for you. You put a proxy in front of your websites, and it will take these URLs and say, hey, he asked for www.example.com/news, but that particular part of the site is served by machine A, right? And www.example.com/finance is served by machine B. So now sort of the proxy becomes a router for you on the layer 7, where it knows about the HTTP protocol. It knows which machines are best to go to for these particular requests. Huge advantage. It makes it a lot easier to write your web applications as well. Unified URLs and let the proxy server act as a router and deal with it. So now the real problem here comes where you have millions of users or hundreds of millions of users, right? And you have all these machines now that have 4 cores and 8 cores and 16 cores and a tremendous amount of CPU power. How do we get all these requests to be processed and managed in an efficient way on this modern hardware? And this is sort of where you go back and look at like traditional applications like Squid might sort of fall off the edge a little bit and not deal with these things. So the couple of things that people would do, right? The first one is multithreading. So you look at something like Varnish. Varnish is a great proxy, but I think it has a flawed multithreading process where basically any connection that's active getting data on it consumes an entire thread. So it's great for parallelism, right? It's easy to write for, but you might be running your Varnish site with 10,000 threads or 20,000 threads. That's a significant amount of overhead to do context switching on 20,000 threads. But it's a great way to solve the parallelism problem, right? There's also another problem with multithreading, and that's it's really difficult to write code for it. It's hard. And I've done it, and I still think it's hard. And here's a good example, right? It's so easy to get things like deadlocks and race conditions and all that sort of stuff. And this is sort of things you have to deal with all the time when you're writing this code in multi-threading environments. So people came up with sort of a different solution. This is how Squid works, and Node.js is very popular these days. They do this sort of asynchronous event processing, event loops, right? Now this runs within one process, and it's much easier to work with because you don't have to deal with any of this locking and potential race conditions and deadlocks and all that stuff. Things just sort of spins in a loop. You create new events. It checks for new events on the sockets and all that sort of stuff, and magic just happens, right? Really easy to program for. That's why people love Node.js, because it's so easy to work with. Great system. I like it a lot. There's a problem, though, however, right? This doesn't solve the concurrency problem. Typically, an event processing is only going to use one CPU. Okay, so now you start doing things like multiple processes. So you look at Nginx, right? Nginx does this. It starts up 2 or 4 or 8 or whatever, some number of processes, right? Now you have to deal with resource sharing across processes, and context switching on processes is much more expensive, and so on and so forth, right? So a little bit of a mixed bag there as well, where, yes, it's easy to program for, but it's probably not the most efficient way of doing things. So what do we do for Traffic Server? Well, we decided to go the worst possible route. We did both. So Traffic Server has a small number of threads. Each one of those threads, and that's the blue threads here in this picture, each one of those threads is an asynchronous event processing machine. So what that means is your typical machine, you will set up 1 or 2 threads per CPU, and Traffic Server will scale this for you automatically. And it will basically run one of these asynchronous event processing things per thread. So a typical box will see maybe 16 or 24 or some small number of threads. Lot less overhead than you see in Varnish. It can deal with a lot more concurrent clients, right? We tested up to 100,000 concurrent clients on a server. You basically become memory bound because each connection will take some amount of memory. So it's a great model, but it actually makes it really difficult to program for. So we have some rocket scientists working on some of these stuff in the code itself. And it's very efficient, it's very fast, but it is difficult. So configuration and managing the software, it's always, I mean, this is what it looked like before I started working with proxy servers. And I mean, now I look like this, right? So it's not pretty. And people go down and download Traffic Server and they say, oh my God, this totally sucks. Look at this. I mean, here's a small subset of the config files that we have, right? It looks like a nightmare. How can anyone configure all this stuff? It's impossible. But here's the good news. There's really only 3 files that matters. Records.config, storage.config, and remap.config. Those are the 3 files that most people will actually be looking at when they start installing Traffic Server and working with it. Records.config is a normal key value pair storage. That's where sort of all the flags and numeric parameters and how much cache size you're going to use and that sort of stuff. Really straightforward. All the configs have good names. You can pretty much read the config file and understand what the configs will do. There's plenty of comments in there. You can understand what the comments say and set up a typical server. Now, the good news is, too, that most of the configs out of the box are good. You can actually take almost all the benchmarks. All the benchmarks I did in the first one is actually using the default configs. I didn't tune anything. It just works automatically out of the box. So that's a great feature, I think. The second one is storage.config. And this is the one that you do have to configure yourself. There's no choice here because the server can't really sort of magically figure out what storage you have, right, or which part of your disks do you want to use for disk storage. So this is one of the places you are going to have to go in and put some stuff in there. And the last one, if you're using a reverse proxy, you're going to have to do a remap.config. And that's basically telling when the proxy sees a URL of a certain format, where should it send these particular requests down to. So this is a good file. It's a useful file that you're almost certain going to use in a reverse proxy environment. So in records.config, when you open it up, you'll be kind of shell-shocked a little bit. You're going to see 600 configs or whatever it might be, some large number of configs. The good news is, I'm showing a few of them here. The good news is, out of the box, it's pretty much default to set up for you. This is actually what the defaults are. And for a reverse proxy, these are the 3 things that really matters. You want to decide which port you're going to be on. You need to enable a reverse proxy, and you want to say require remap rules, right? If you don't do the last one here, the require remap rules, it actually ends up becoming a forward proxy. So that's sort of the only 2 difference between reverse proxy and forward proxy. The only config change you have to do is changing that one particular setting. Be careful, if you're setting up a forward proxy, if this thing is out on the wild, right, on the internet, people are going to find it within hours or minutes and start abusing it as an open proxy. So if you're setting up a forward proxy, you want to make sure that you use some sort of firewall or IP tables or something on the box to protect it. So we talked about remap.config. Remap.config is sort of the generic way of mapping rules in a reverse proxy. I'm not going to go into a huge amount of details here, but the examples are basically when the server recognizes a particular set of URLs, in this case /CSS, right, route that to a different set of machines called css.example.com, and everything else would go to maybe the sort of back-end origin server for the content. Note that order here is important, right? You need to make sure the one that's going to be the most sort of matching rule comes first, because if you switch the order on these 2, then the first one will match the second one as well. So everything will get sent to real.example.com. You can also do reverse mapping. What reverse mapping really does is change the location header in the responses. So if a server sends back saying, I'm real.example.com, and the location header in a 302 redirect says something real.example.com, the reverse map will make sure to rewrite this back into the real URL again. You can also do regular expression matching on the URLs. This is a powerful tool if you have a lot of sites, right? If you have tens or hundreds, like Yahoo has well over 100 different sites, it might be useful to be able to do regular expression matching on the URLs. Some other interesting features of I'm not going into all of these, but we have a fair amount of interesting cache features. The disk cache is extremely low overhead. It actually uses disk on the raw device, meaning it bypasses the file system. It also has an extreme low overhead on memory consumption, whereas Squid would use maybe 60 or 70 bytes of memory for every object on cache, disk cache. Traffic Server will use 10 bytes. And I think it's even worse for Varnish. I think Varnish, the minimum, at least it used to be, it wouldn't consume anything less than a kbyte of memory. So this is one of those things you need to look into. If you have a lot of objects in your cache, you have very large caches, say terabytes of disk cache, this is one of those considerations you need to be aware of. We do support different types of eviction algorithms. It's not as flexible as Squid. Squid is very good at this in this space where it can actually be configured to do all sorts of interesting eviction algorithms. We do have two algorithms in the disk cache on Traffic Server. One is a simple LRU, and the other one is what we call the CLFUS. And the CLFUS is the one that's on by default. And what it tries to do is to avoid churning through the LRU, right? So if you have something that's scanning the cache, things doesn't get promoted up to the top of the LRU. So it sort of keeps a little bit of counters before things get promoted and demoted into the cache. A little bit more intelligent. Same concept as an LRU, though. So where are we going with Traffic Server? Well, we've been trying to do release early, release often. Last year we did over 10 releases. And it sounds like a lot, but I think it's actually really useful because it makes it easy to get new features and bug fixes out there, out to the users, and have it happen fast. We work on IPv6. It does IPv6 today on the client side, meaning you can do what's called NAT6, I think, where you can have clients talking IPv6 to the proxy server, and the proxy server will NAT that into IPv4 on the back end. This is a great way to deploy IPv6 initially, right? You don't have to go out and maybe change tens of thousands of servers to do IPv6. You put a couple of proxies out there, put IPv6 on the front end, and talk IPv4 to the back end. This is actually how Yahoo did the IPv6 days last summer. Now, they didn't see any traffic, but everything worked fine. What else are we doing? We're doing more SSL improvements. It's one of the areas we're lacking a little bit. We need to get some of the new stuff like NPM, the next protocol negotiation, server name, something, and a bunch of other SSL features needs to go in there. This is being worked on. We're hoping most of this will go into the next major revision, 3.2. This slide is, I guess, a little bit old. We did already do improved memory management. You can also use JEmalloc and TCmalloc if you want to. However, in most cases, you're not going to see any benefits of doing that. Because here's one of those things that we were clever, right? If you look at Traffic Server today where you sort of trace a request through the proxy server itself, there's not a single memory allocation at all. And this is great for performance, especially in a multi-threaded application, right? If you avoid memory allocation, it doesn't matter which allocator you're using, because it's not going to get cold anyways. Where you can use JEmalloc and TCmalloc and other better allocators would be, for example, in plugins or things which you, for some reason, need to go in and do memory allocation on the heap. But Traffic Server itself would not benefit from that. We are working on optimizations for SSDs where today we have a memory cache on top of a disk cache, right? That's all that we have. What we want to do long term is to put SSDs sort of in between here, where you might have, say, 10 terabytes of rotational disk space and 48 gigabyte of RAM cache, and maybe you want to put in 1 terabyte of SSD drives in between. So what's going to happen when we get this done is that objects will get promoted up and down this sort of stack of caches. And hopefully the really, really hot objects will get into RAM cache, right? And those that are sort of medium hot, somewhat hot, they'll get into the SSD, and everything else stays on the rotational disk drive. This will get you better performance and more scalability where, let's say you do need 10 or 20 or some large number of terabytes of disk, right? You're not going to be able to afford to buy, unless you're Arthur Bergman, you're not going to be able to afford to buy that much SSD. We're also working a lot on the plugin APIs. I didn't touch on that at all here today, but one of the strengths of Traffic Server is that we have a very, very complete and sort of functionally useful API where you can do a lot of changes to the way the proxy server works through plugin APIs. Now, this is an evolving process where as people start using it more and more, we're finding out that we need to add to these APIs. And one of the things that we really need to get done is a load balancer plugin. So I'm hoping that we can get someone to work on that pretty soon. All right, so now the question, was this all a huge waste of time? Well, I think it wasn't, and I hope it wasn't. And I'm going to tell you why I think so. Traffic server in general, and proxy servers too, are really useful tools, right? If you don't know that you have these tools, you're missing out on it. You should be looking at using these in your infrastructure. If you're doing anything HTTP related, you should be looking at proxy servers in general. And hopefully you'll look at traffic server too, but if anything you take out of this presentation is that you should look at proxy servers, I think it's a huge win. And traffic server is fast. It's ridiculously fast. We benchmarked it at some machine, some crazy machine that Yahoo had. They benchmarked at 220,000 requests per second. That's out of cache. They benchmarked it with no cache, basically acting as a router. A proxy was doing 100,000 requests per second. So, and this is true for pretty much any proxy out there except Squid probably. They're going to be outrageously fast. So performance is not really the issue here. But they are fast. Traffic Server is part of a vibrant community. It's an Apache Software Foundation project. And I know Apache has been getting a bunch of slack lately because of the Git versus Subversion and that sort of stuff. And if that's the biggest gripe you have against Apache, that would be awesome, because it's just a tool, right? I use Git on top of Subversion. I have a problem with that. But it is a great foundation. We have a lot of people there that do great stuff, lot of smart people. For Yahoo to contribute a traffic server to Apache was a huge win, because as soon as we did that, we saw like 10 or 15 developers coming in, looking at the code, working with the code, and it's been a huge success. Huge success. So finally, Arthur Bergman always tells everyone, if you're not using SSD drives, you're wasting your lives, right? It's a great thing to say. I mean, SSDs are awesome, but here's the thing. If you're not using a caching proxy, you're probably wasting your SSDs. So that's all I had today. I also like to thank my company for letting me come out and do these sort of things. I'm having a blast working for GoDaddy, a great company to work for. Thanks.
All right, we have a few minutes left for questions, 10, 15 minutes. If anyone would like to ask anything, just come up to the microphones.
So I've done a lot of work with proxy servers in various and sundry implementations, and two of the features in proxy servers that seem to chew up most of the valuable resource is header injection and URL rewrites. And I didn't see either one of those in your services. Are you guys looking at that, or do you have a recommended solution for it?
Well, so URL rewrites it does through the remap.config.
I'm sorry, content, not...
Content.
Yeah.
Okay, so the first one, header manipulation, it's actually extremely fast doing that. I don't have any numbers for it, but in most cases it's going to be insignificant. The way we manage headers inside the code, it's using marshalling buffers, and you actually end up just changing pointers basically, so it's extremely efficient. For content manipulation or say basically rewriting HTML or rewriting JavaScript or doing gzip compression, that sort of stuff, there is a plugin API to do that. You can write your plugin, and basically what you do is you end up putting your plugin as a sort of filter in the stream of data coming through from the origin down into the back to the user. And the way it works is actually pretty efficient in that when you do a plugin like that, the plugin can tell, hey, this content should be cached or not cached. And if you tell it to cache it, it will write to the cache at the same time as it's sending it up to the client as well. So now it's a little bit difficult to write these particular types of plugins, especially these are called transformation plugins. They take a fair amount of work to do, right? Especially the way traffic server is done, right? Remember, it's multi-threaded and asynchronous event processing, so you're not allowed to hog the thread for longer periods of time. So you need to yield back to the event processor and that sort of stuff, which makes it a little bit complicated. But there are examples. If you go download the source code, there's an example to do gzip compression, for example, and that's typically what people would do, right? Stuff like that. Any other questions? All right. Well, thank you.